The Advanced Manufacturing Laboratory, or AML, is part of the Livermore Valley Open Campus, an innovation hub where Livermore researchers collaborate with partners from government, industry, and universities. The lab has developed some of the world's most advanced manufacturing tools and materials, and many of these are housed right here. This gives collaborators access to specialized resources to tackle the manufacturing challenges behind both commercial and government projects. In short, the AML is an incubator for innovation, where new ideas and new technologies take shape. This is our 4,800 square foot wet lab, designed to be easily reconfigured for shifting projects and collaborations. The first few benches are often busy with researchers mixing reagents or running characterization experiments. Many of the machines here are used for materials characterization. That's the process of testing how a material behaves, how viscous it is, how much heat or light it needs to cure, or how dense it is. These factors are crucial for deciding which 3D printing method is best for printing a new material. Other machines are used for part characterization, making sure a 3D printed structure is as strong or as flexible as its intended use requires. This machine extrudes the microcapsules used in a partnership with the company Artvioli. These tiny spheres contain algae and a special solution that captures carbon dioxide as soon as it touches the air. Artvioli mounts the multicolored capsules on flat panels, creating works of abstract art that also improve indoor air quality, making buildings healthier spaces. Projection microstereolithography, or PUCL, is one of the most common resin-based 3D printing methods. The process begins with a computer model of the structure, which we slice into thin layers. We spread a thin layer of liquid resin onto a platform and shine UV or laser light in the pattern of the first layer, solidifying it. Then we add another layer of resin and shine the light again. We repeat this until the full structure takes shape. AML has multiple versions of this system, some built in-house, others commercially purchased. With our Livermore-built printers, we're expanding the range of usable materials, improving print speed, and increasing resolution. We also collaborate with manufacturers to help enhance their own systems. This large blue structure is called MARS, short for Modular Autonomous Robotic System. Autonomous lab systems like this rely on machine learning to function. One of the most common 3D printing techniques at Livermore is direct ink writing, or DIW. This extrusion-based process prints inks directly onto a surface to build a 3D structure. One major advantage is its material flexibility. We use direct ink write with polymers, ceramics, biomaterials, metals, and even glass. You just need to make an ink version of the material, something you can then squeeze out like toothpaste. The other advantage is that we can print on curved or complex surfaces, not just flat ones. That means we can add material to existing parts rather than always starting from scratch. Volumetric additive manufacturing, or VAM, is true 3D printing, and it looks like something straight out of science fiction. Traditional 3D printing builds layer by layer. VAM creates the entire structure at once. The process works in reverse from CT imaging, like a CAT scan. In CT imaging, we scan a real object to create a digital model. In VAM, we start with the digital model and reverse the math to generate light patterns that shape the structure. Those light patterns shine into a liquid resin, curing it into a solid part. It's much faster than traditional printing, minutes instead of hours or days. Livermore began exploring light-based additive manufacturing in 2008, developing our own technologies and partnering with others. In Room 1101, we conduct experimental metal additive manufacturing, which requires extensive modeling and simulation alongside the builds. This dry lab features an anti-static floor and covered outlets because the fine metal powders we use can pose an explosion hazard. The room also includes 1-hour fire-treated glass to contain any flames if necessary. This is a directed energy deposition machine that prints metal parts using a laser instead of a powder bed. What makes it special is a custom setup with 16 mini hoppers, each holding a different material. Here's how it works. A nozzle sprays metal powder while a laser melts it, solidifying the metal as it's deposited. As the nozzle moves, the 3D metal structure gradually builds layer by layer. We can feed up to 16 different metals into the nozzle in any combination. That allows us to create new metal alloys and customized parts with enhanced properties, like strength or heat resistance. This SLM 280 machine was designed specifically for that purpose. A thin layer of metal powder is spread onto the build plate, and a laser traces the first layer, solidifying it. Another layer of powder is spread, and the process repeats, layer by layer, until the structure is complete. Inside these laser curtains are our research versions of the process, called Dium and Flame. Commercial machines are enclosed for safety, but in our research systems, scientists can access the lasers directly, so they're kept behind protective curtains. Researchers can adjust laser power or wavelength to improve printing methods. These systems also help validate our 3D printing models that predict part performance. The M2 machine you see here is another laser powder bed fusion system, originally loaned to us by GE. It allows us to integrate in situ monitoring into a process called intelligent feed forward, which makes printing more reliable. Instead of pressing start and coming back 2 days later, hoping the part printed correctly, the M2 can provide real-time feedback. If something goes wrong early in the build, we can stop and restart. If an issue happens near the end, we can make small adjustments to save the print. In traditional manufacturing, losing a few parts out of 1,000 isn't a big deal. But in 3D printing, where only a few parts might be made each day, losing even one can be costly. Monitoring and correction can help prevent that kind of loss. This machine is a 2-photon laser system that prints at the nanoscale. It uses polymers and ceramics to create some of the smallest 3D printed structures in the world, about 1,000 times thinner than a human hair. A 3D build just 1 centimeter tall can take up to 2 days to print. The Advanced Manufacturing Laboratory is where Livermore and its partners come together to accelerate innovation, reduce production costs, and shorten development time, while partners contribute their expertise to projects vital to the lab's missions.